In the first section of this lecture, we closed by noting the map that shows the distribution of land and water around the Earth, and the curious phenomenon that it appears that these two great supercontinents of the New and Old World might actually fit together like two pieces in a jigsaw puzzle. This phenomenon was noted as early as the 17th century, but not explained until the beginning of the 20th century. Pictured here on the left is Alfred Wegener, a German meteorologist who, along with his Eskimo guide, studied the climates of the polar regions. In 1930, this last photo was taken of Wegener before he attempted to head across the icy surface of Greenland, where he froze to death. But Wegener is remembered not so much for his meteorology as his contributions to geology. For in 1915, he published a book that first explained the theory of continental drift. In Wegener's version, the continents once fit together, as pictured here, in a vast, unified landmass he called Pangaea, which broke up about 160 million years ago, and its pieces began to move to their present location. Wegener was not just fabricating this idea, for he based it on his knowledge of similar geological formations and biological types along the eastern edge of Africa and the western edge of South America. Still, no one bought into this theory because there was no force considered strong enough to drive these continents through the seas to their present location. The intellectual breakthrough that transformed and proved this theory occurred after World War II, when transatlantic shipping, equipped with sonar devices, began to map the floor of the Atlantic Ocean. This mapping revealed the existence of a mid-oceanic ridge running the length of the North and South Atlantic. Moreover, the more scientists observed this ridge, the more they discovered that the rock nearest the ridge was younger and hotter than the rocks further from the ridge, which were older and colder. This observation led to the theory of seafloor spreading, as illustrated here. Under this theory, a crack occurs along the mid-Atlantic ridge, and magma escapes like toothpaste through a tube, forcing its way up and through the crack and separating the ridge, pushing it in both an easterly and westerly direction. Hence, the rock nearest the ridge is younger and hotter than the rock formed and migrating further from the ridge. The theory of seafloor spreading was given further confirmation by the mapping of earthquakes and volcanoes around the world, as illustrated here. You'll note that one line of earthquakes and volcanoes runs right down the middle of the mid-oceanic ridge, first in the Atlantic and then other ridges discovered in the Pacific and Indian Oceans. This phenomenon, the formation of these earthquakes and volcanoes, follows naturally from the theory of seafloor spreading. For as the magma forced its way through the crack in the earth, it did not spread the earth smoothly and evenly, but because it had to overcome the friction between the rocks, would build up pressure, and finally the rocks would snap, a snapping that causes earthquakes, and then the magma would seep through the crack in the earth, forming volcanoes. Moreover, this mapping of earthquakes and volcanoes shows that not only is there a particular distribution of these phenomena along the mid-oceanic ridge, but they also lie in further afield. scientists have deduced that the secondary location of earthquakes and volcanoes is formed by the collision between what are now viewed as tectonic plates or pieces of the Earth's crust that are moving outward from the mid-oceanic ridges. And since the Earth is a sphere, if it is expanding in one area, it must be colliding in another. These collision zones form the secondary earthquakes and volcanoes that are seen on the far side of the tectonic plates. Notice this map of the tectonic plates, that each plate includes both oceanic crust or basaltic crust that forms the basis of the oceans, as well as granitic or continental crust that makes up the great continents. As a consequence, as these great tectonic plates move, there are three possible types of collisions between them. There can be, first of all, a collision between oceanic and continental crust, as is illustrated in this map, between the western edge of North and South America and the Pacific plates, where the continents of the Americas collide with the seafloor of the Pacific plates. Or there can be a collision between continental granites and continental granites, as occurs here when the Indian plate moving north collided with Asia, forming a massive collision zone between these two great continents. Or thirdly, an oceanic crust can collide with an oceanic crust, as occurs in the Pacific Ocean when the Australian plate moving from west to east collides with the Pacific plate. In the following section of this lecture, we'll take up these various types of collisions.